Hi viewers, welcome to my channel on quantum physics. This is my second episode in my lecture series. Well, I'm R. Priya, Professor of Physics, Department of Science and Humanities, RMD Engineering College, Kavarapetai. I'm sure that this lecture will be very useful to you. In this lecture, I'm going to discuss about Planck's quantum theory of black body radiation. This picture you have already seen in my last video. This clearly tells about the drawbacks of classical concepts. Ultraviolet catastrophe is the error at shorter wavelengths or in the longer range of frequency in the Rayleigh-Jeans law for the energy emitted by an ideal black body. As a solution to all these problems, Max Planck gave his modifications based on quantum concepts and was successful in deriving an equation suitable for the entire range of wavelength or frequency. Let us see the assumptions made by Max Planck. Black body contains electric oscillators of all frequencies, and these oscillators are responsible for emission and absorption of radiation. Energy changes should take place discontinuously or discretely. The energy is always integral multiples of small indivisible unit or packet called energy quantum. The quantum of energy is directly proportional to the frequency of the emitted radiation given by the equation E equal to h nu, where h is called Planck's constant, whose value is given by h is equal to 6.625 into 10 power minus 34 joules second. To start the derivation, let us consider a system composed of many oscillators. Let capital N be the number of oscillators with total energy Et, and the average energy of an oscillator E bar is given by E bar is equal to Et by N. If N0, N1, N2, etc. are the atomic oscillators of energy 0, E, 2E, 3E, etc. respectively, then the total number of oscillators N is written as the sum of N0, N1, N2, N3, etc. as shown in the equation 2. The total energy of the oscillators can now be calculated by taking the product of the number of oscillators with that of the corresponding energy. Sum up all the values, we get equation 3. According to Maxwell's distribution formula, the number of oscillators having an energy Re is given by Nr is equal to N0 exponential minus Re by kBt, where kB is the Boltzmann's constant, R takes the value from 0, 1, 2, 3, etc. The number of oscillators corresponding to various values of R can be calculated as shown in the equation 5. Substituting equation 5 in equation 2, we get this equation. Now in this, N0 can be commonly taken out and we get this equation. We know from the finite geometric series that 1 plus x square plus x cube plus etc. is 1 plus x power n plus 1 by 1 minus x. Whereas if x is taking the value between minus 1 and plus 1, the equation gets reduced to 1 plus x square plus x cube plus etc. which is given by 1 by 1 minus x. On applying the above mathematical series to equation 6, then we get this equation as n is equal to n0 into 1 by 1 minus exponential minus e by kBt, which is termed as equation 7. Similarly, on substituting equation 5 in equation 3, we get this equation. On simplifying, that is taking n0 e exponential minus e by kBt commonly outside, we get equation 8. Again, equation 8 is similar to a finite geometric series that is 1 plus 2x plus 3x square plus 4x cube plus etc., which is equal to 1 by 1 minus x the whole square for x taking the values between minus 1 and plus 1. On applying the above mathematical series, equation 8 becomes Et is equal to n naught e exponential minus e by kbt into 1 by 1 minus exponential minus e by kbt the whole square. Substituting equation 7 and equation 9 into equation 1, that is the average energy equation, that is E bar is equal to Et by n. We get equation 10, that is E by exponential E by kbt minus 1. Now in this we can substitute E is equal to h nu. So E bar becomes h nu by exponential h nu by kbt minus 1, which is termed as equation 11. This equation represents the average energy of the oscillator. According to Rayleigh distribution formula, the number of oscillators per unit volume within the range of frequency from nu and nu plus d nu is given by capital N is equal to 8 pi nu square d nu by c cube. Therefore, the total energy per unit volume or energy density E nu d nu is equal to N into E bar. Substituting equation 11 and equation 12 in equation 13, we get E nu is equal to 8 pi h nu cube by c cube into 1 by exponential h nu by kbt minus 1. This equation represents Planck's radiation law in terms of frequency. Now we have to convert this into wavelength. So by simplification, that is by taking nu is equal to c by lambda, we can change the equation 15 as E lambda is equal to 8 pi hc by lambda power 5 into 1 by exponential hc by lambda kbt minus 1, which is taken as equation 16. This equation represents Planck's radiation law in terms of wavelength. This formula agrees well with the experimental curves in the whole range of wavelengths. From this formula, we can deduce Wien's displacement law and Rayleigh-Jean's law. Now let us deduce Wien's displacement law first. We know that this law holds good only for shorter wavelengths. So we take the lambda value to be small and you consider equation 16. I am giving this equation 16 for your reference at the end of the slide. You can see here. So in this, lambda appears in two places. One is outside the bracket, the other one is inside the exponential. So we have to give importance only for the lambda present inside the exponential term. And inside the exponential, it is a ratio and lambda is appearing in the denominator. So when lambda is small, the ratio becomes large. Exponential of a larger value will be much greater than 1. So 1 can be neglected. So equation 16 becomes E lambda is equal to 8 pi hc lambda power minus 5 exponential minus hc by lambda kbt, which I will write as C1 lambda power minus 5 exponential minus C2 by lambda t, which is shown as equation 17, where C1 and C2 are constants whose value is given as C1 is equal to 8 pi hc and C2 is equal to hc by kb. Also, t is inversely proportional to lambda and E lambda is proportional to lambda power minus 5. Therefore, E lambda is proportional to t power 5. So, we are able to get the Wien's displacement law completely here. Now, we will see how Rayleigh-Jean's law is deduced from Planck's theory. We know that this law holds good only for longer wavelengths. I am giving equation 16 for your reference at the end of the slide. I am showing that equation in red color. You can see where lambda is present. As I said earlier, lambda presence should be considered inside the exponential series. So we can see a ratio is present in the exponential and lambda is in the denominator. So when lambda is large, hc by lambda kbt becomes much lesser than 1. So the exponential term can be expanded using exponential series. So applying exponential series, I am getting e power hc by lambda kbt is equal to 1 plus hc by lambda kbt plus half into hc by lambda kbt square plus 1 by 6 into hc by lambda kbt cube plus etc. For larger values of lambda, higher powers of hc by lambda kbt would be very small and hence it can be neglected. Therefore, the above equation becomes exponential hc by lambda kbt is equal to 1 plus hc by lambda kbt. Now on substituting this equation into equation 16, we get E lambda is equal to 8 pi kbt by lambda power 4. So this equation represents Rayleigh-Jean's law. So thus Wien's displacement law and Rayleigh-Jean's law can be deduced from Planck's radiation law. Thus Planck's quantum theory of blackbody radiation is able to give one equation for energy distribution for the entire range of frequency, thus overcoming the problem due to the concepts of classical physics. To watch my previous video, please use the following link. And in my next episode, I would be discussing about Compton effect. Thank you for your attention.